Can I use this? Yes, okay. Good afternoon, everyone. In continuation to what Chai said about the cognition of aging, I can say that some very wise old men used to say that you are old when you have less dreams than you feel aged when you have more achievements than you have dreams. That was Shimon Peres, zichrono levracha. Okay, and from this I will take you to my talk about the embryonic form of life, about regenerative medicine. What we are trying to do in my company, BioChange, is to regenerate everything, every tissue and every organ in a similar way that we did that initially at the embryonic phase. So we all are well aware of the problem that if we get an injury, either it can be by aging, by disease, by trauma, whatever, and we have a severe damage to a tissue or an organ, our body cannot repair itself. It can maybe do it cannot regenerate itself. It can do minor repairs, very minor repairs, which usually, if it's too much, if it's too extensive, it ends up in a scar or in deformations of the tissue, and there are many that are left with damages. So we did do it initially, right? Every one of us was able to do this when we just started. So a ball of cells, a blastocyst, within 5 to 6 weeks, developed everything, all the organs, all the multi-level complex structures and functionality within just 5 to 6 weeks. So how did that magic of life happen? Okay, so this is a smart material, the smartest material that we know of. Without any intervention, it can just form everything. And they also know when to stop. Every finger, every eye, every spine knows exactly where to go, what size and what to become. So how is that possible? And it's not only possible during the embryonic phase. It turns out that there are several, jumped a bit. There are several various animals in nature that can do it when they are adults. Okay, for instance, the axolotl. It can grow its arm again and again and again and again, about 5 to 6 times during his 13-year average lifespan. How is it possible? So let's see. When they have an amputated limb, instead of scarring, they have epithelium that covers the external damage, and then there is recruitment of undifferentiated cells, or in other words, a biological reset, which is exactly similar to the embryonic phase of limb buds growing and emerging into a full limb. They call it a blastema, okay, similar to the blastocyst. And again, every cell just know where to go, what to become, to turn into a joint, and that's a vertebrate. It's very similar to us, actually. Another less advanced, but really super interesting creature is the planaria, is a flatworm. So that's kind of like an extraterrestrial. It's really unbelievable what they can do. If we cut them into pieces, they will grow a new planaria, okay? Those animals can be cut into 245 units, and they will grow 245 new planaria. That's how they multiply also. And they are very, very extremely adaptable to wherever they are around, okay? So a manipulation was done, a bioelectrical manipulation was done many years ago, by the way. They cut them in the middle and they made them grow, instead of another tail, they made them regenerate another head. So that's a 2-headed planaria, okay? That you see here, and it survives, it's alive, it's doing well, okay? Now, just a few years back, somebody asked the question, so what will happen if we cut the 2-headed planaria in the middle? Will we get 2 planaria which have a new tail, like the original blueprint, the original design? And no, the interesting thing is that if you cut the 2-headed planaria, you get another 2-headed planaria, okay, regenerated. So that's fascinating, because that the paradigm was that all that information sits in the DNA, but it's the same DNA, the single-headed planaria and the newly designed new-headed planaria, double-headed planaria. They have the same exactly DNA, but there is another layer of information processing here, which is done at the cellular level, and it's not only the DNA that defines it, and that's a really important fact to understand. So cells are not just a building block of life. The cells are actually our information processing units. Every one of them receives informations, and then it processes and does something with that information. And for them to synchronize, they need really, really strong communication between them, especially at that embryonic phase when they need to grow all those structures together, right? And what you see here is a zebrafish. Okay, the embryo of a zebrafish can be imaged. It takes them just 1,000 minutes, that's it, to print. It's not really printing, but it's to develop all that, the organism itself, the full organism. So if we are talking about communication between the cells, okay, we need to understand there are three ways for the cells to communicate. The one that is already known 40, 50 years and researched a lot is the biochemical way. But that's not enough. Recently, there's information about the bioelectricity, bioelectrical synchronization. So not only neural networks can have intelligence and can solve problems, but also more simple biological system like cells, even biofilm can solve problems. Okay, so in this case, we see cells solving problem in morphospace. They know how to go, where to go. They can, even if they have some damages on the way, some mistakes, they can correct it. So there's a newly discovered information transfer technology, which is the biomechanical one, and that's where I'm going to focus and show you more, okay? So it turns out that during that initial organogenesis phase, the extracellular matrix is actually arranged in a foam structure. Then it turns into the fibers that we know in the adult tissue. So why foam? The foam has very unique biomechanical properties. And why fibers? Well, that's kind of obvious, because as we develop the tissues and mature and we need to prepare ourselves for the external world, the fibers are much more robust than the foam. So we trade off to be persistent and robust in the outside world, but we cannot do the regeneration very well again. There is a lack of communication between the cells, or the bandwidth just reduces over time in that structure. So what we see, So a really brilliant researcher named Roger Campas, what he did to research this biomechanical thing, he injected ferromagnetic oil droplets in the extracellular matrix of that zebrafish, and then he manipulated with external magnetic forces on the droplet that wants to come back and become round. And I'll show you just the bottom line. He discovered and uncovered that cells actually communicate through that foam. They tingle the foam, they vibrate. So the vibration are codes of information. We don't know what the hell they're talking about, but you can see them speaking to each other and synchronizing the growth of that new organism, right? And that's what we want to do. We want to bring back the ability of cells to communicate with each other, and we developed the cell foam technology in biochange, which is just the foam. So our approach is very simple. We don't know what all that biological intelligence is doing and how it's doing. We look at it like a black box. We're not going into micromanagement of all the processes. We're just providing the cells communication device so they can speak with each other again, talk about what they want to build, about navigating that morphospace. The cell phone looks like this. It can come as an injectable that can be mixed at the point of care. I'll just jump real quickly. And it sets inside the body, and it becomes this really nice, flexible foam. It has very unique biomechanical properties that we engineered it to be. It has a non-linear elasticity, and it vibrates very well. So we are developing a line of products from this foam. We've started with pet care, veterinary. We have 3 products in veterinary care in the market, and growing revenues from those products. Our best product there, our most successful one, is for regenerating the periodontal tissue, regenerating the gums after periodontitis. Then the next stage would be the dental, okay? Bringing that same solution to human. this is going to be FDA approved by next year, okay? How did we do it? Because the FDA considered this a simple medical device with low risk, so we are able to do it in a 510K pathway, and they don't even require clinical studies. So we are on a fast path to get that done and get this product to humans by 2027. It will be available. The next thing would be aesthetic and plastic surgery, and we've done feasibility in many other fields. I'm not going to get into all the fields right now because I don't have enough time. I can just say that I'm kind of optimistic, but I know it's not science fiction, but it's not going to happen tomorrow, that we'll be able to regenerate complex organs, like even hands, legs, everything. So far, we have a substantial amount of preclinical data and veterinary data in skin, in bones. In skin, we are able to regrow or stimulate the skin to regrow itself. Even you can see new blood vessels inside the pores of the foam. We see elastin fibers as well. We see young-looking morphology of the stimulated fibers. In the bone, we did some models as well here, and we've also been surprised to see. Why surprised to see a very good bone stimulation? Because the normal scientific paradigm in the field of biomaterials is that you need a soft scaffold to regenerate soft tissue, and you need a strong, stiff scaffold to regenerate bone. But no, it's exactly the same soft scaffold that regenerates the bone. So we have, since March this year, we have FDA approval for veterinary care. I've mentioned that. And some of the results that we get back from veterinarians is astonishing. In the left, you can see a stage 3 periodontal disease. Those teeth needs to be extracted, but no, they said, let's try this new product. It's called the Riga. They pushed it into that forcation. That's the arc under the root. And voila, 1 year later, we've been able to recover the bone line, save the teeth. And we can also do other things like with bone, fractures. There are many, many applications of it just in dental. And another very important point to make, that even if we're just able to do just this application and no other things, we're going to extend human life expectancy, because there's a ton of evidence that shows the relationships between periodontal disease and aging and other cardiovascular disease, even Alzheimer and Parkinson. The second product is going to be, this is still the first product, periodontal disease. I'm just going to add one more thing about it, that's not just one tissue. We're talking about 4 tissues here. A simple organ, you can call it, but it's not just one tissue. And we are able to regenerate all of those tissue. We have studies that were published. You can look them up. It's later on. I will provide the link. We've been able to build back bone line, build back the soft tissue, the pocket. And an important point here to make is that if you can see in the upper right image, that's the standard of care today in bone grafting in dental. They put in the bone graft, and then they cover it up with a membrane that they call guided tissue regeneration membrane. Why guiding the tissue is needed? Because normally the soft tissue, the gingiva, grows 10 times faster than the bone. So it just grows into the bone graft, disrupts the bone from growing, and we don't get bone grafting. That's why they use 2 products. In our case, we didn't do that. They thought we are crazy when we did the initial studies. It's not going to succeed, but it did succeed because we put in the foam and it synchronizes the cells that they don't compete anymore. They speak with each other, the osteoblasts and the fibroblasts, whatever, and they build back all those structures and all the tissues. The next product that we will bring to the market is the injectable for aesthetic dermatology, or making our skin young again, and a reconstructive surgery that will take more time. And we have also substantial amount of evidence here, mainly in pigs, to show that we are better than any other biostimulator or scaffold which is out there. We are also, and this is new data not published yet, we've done also experiments in pig where we did the lumpectomy model. We removed the part of the breast tissue and we placed in a spherical shaped foam unit. And we were able to regenerate mammalian glands, milk ducts, And as far as we know, there is no other technology that can actually stimulate regeneration of mammalian glands and mammalian tissue and that's our own tissue. It's not, I didn't mention, but the foam itself is made from gelatin, cross-linked enzymatically. The body dissolves it, degrades it within about 3 months. So it's gone, and we'll get new tissue in place of it. And by the way, Ovatz and his team did methylation clock analysis on the axolotl, on the regenerated limb, and he showed that the methylation clock restarts itself in the new limb. So maybe if we can regenerate new organs, we'll be able to do it many, many times and have young organs instead of those aged one and defected one. So I just want to thank my team and our collaborators. And you're welcome to, this is, I think, a link to my LinkedIn page. You're welcome to follow up. And we'll make America young again. We're on the way. We'll get FDA approval in a year or so. But not to get into politics, it's not only for America, it's for everyone. Okay, so thank you very much. I'll be happy to take some questions.
Yes. Thank you for this amazing talk. It really looks very applicable and amazing results. I just have a question regarding to how come the body does not reject external scaffold that is injected to the body. And you just mentioned in your last part of the lecture that after 3 months, you said? It dissolves, so you need to reintroduce it to the body?
Those are good questions. The body does sees this gelatin as a foreign body, but the immune response is very benign, okay? There's no adaptive response to the gelatin. Gelatin is a strange material. It doesn't exist in nature. It's derived from porcine collagen, okay? And it's much less actually immunogenic and is better as a medical device, as a biomaterial, than the collagen itself. So gelatin, that's what we chose to engineer this foam construct foam. So the body does remove it, mainly macrophages, giant cells, they come and they take away pieces of the foam until it's gone. And we call this the remodeling phase. By the time it's gone, we have new tissue already in place. It just synced. That's how we engineered it, to be synchronized with the degradation. The build of the rebuild, the regeneration and the degradation are synced to each other.
Okay, and it's happening without growth factors that it added to the scaffold.
We are not doing anything with any biology here. We're just providing a mechanical scaffold that it's a communication device. Okay, it's a signal transduction for cells. That's all. That's it. So no biology, no cells. By the way, we did do some experiments with using it as a cell laden to deliver cells, living cells, mesenchymal stem cells, and other different engineered cells into the site, and it worked very well in helping them engraft in the tissue. So that can be also a tool for engraftment of all kind of therapeutic, cellular therapeutics. But right now, all the data I've showed is solely only the medical device or just the protein foam. That's it. No hormones.
Okay, thank you.
One question then from me. Am I right that you are using the same matrix, the same form for all these applications? So you're not adjusting it for a particular thing?
We are using the same form for all the applications that I've shown today, except in some cases, it just comes in different physical ways. It could come injectable. For the dental, we ship this in three-dimensional shapes that fits the application site, okay? And I didn't mention, but we already have in the veterinary care more than 40,000 units deployed. So we have obtained a lot of safety and efficacy signal. And I can tell you, we just came back from the American College of Periodontistry and spoke with the top key opinion leaders in the field in America. And they all are very excited about it. And they said that if we are going to see the same outcome in humans as we've seen in canine periodontistry, this is a game changer and a disruptive technology. So in one year, more or less, give and take, we will be able to see what's happening really in real life evidence from humans.
Okay, more questions? Or maybe one last.
First of all, very interesting talk, thank you. And then what I wanted to ask is about the risk of kind of uncontrolled growth. So like, you know, the kind of downside of inducing growth is cancers. Is any uncontrolled growth like cancer?
So we've done some experiments about, with cancer, and we didn't see proliferation of cancer, and kind of makes sense because cancer is the opposite of regeneration. Regeneration, you need like the maximal amount of bandwidth of information and synchronization between the cells, and cancer are cells that decided to disconnect from the collective intelligence of the human body and just doing what's good for them. So if we can reconnect them, we can normalize them, and they will stop being cancer. But we don't have this is just a theory, we don't have evidence on that. But we didn't see any proliferation of cancer when we put it into a model of that sort. We need to do more research on that though.
Okay, thank you very much. It was really a magical talk.